This video goes with lesson 13.7 in your notebook, which is all about dilations. First, we need to define some vocabulary here. In math, the term dilation refers to a specific kind of a transformation. Remember, a transformation is where we take an original figure and change it into a new image. So it's a type of transformation where the figure that we're looking at is either enlarged, that is, made bigger, or shrunk, and that happens relative to a point. So this is where we take a particular shape. Here's an example of it. We're going to take this little square, and I'm going to make it bigger. And I'm going to make it bigger in two ways. First, let's say that I make it bigger relative to this point. Imagine that I'm taking this and I'm using this particular point to make this square bigger. It's like I'm blowing up the square, and this point down here tells me sort of what direction and what shape I'm going to blow it up in. I can also take the same square and suppose that I were to create a dilation relative to a different point. In this case, I'm going to put the point right in the center of that square, and I'm going to make the square bigger relative to that center point. When I do that, I get another bigger square. It just lands in a different location. Both of these are examples of dilation. We say that that point, either this little point here or the point inside of the square there, that's what we call the center of dilation. The center of dilation is the fixed point that shows, and I'm going to put this in quotes, where a dilation happens from. I know that the grammar in that sentence isn't beautiful, but I think it helps us with our math understanding. The scale factor simply tells us how many times larger or smaller an image becomes. And we're typically going to measure this by comparing a side in the image to a side in the original. So if I wanted to find the scale factor for the purple dilation here, I would ask myself, how long is one side in this big purple square? And compare that to how long one side is in the little purple square. That ratio would tell me the scale factor. It would tell me how many times bigger the square got. Whenever we do a dilation, the original figure and the image are the same shape but different sizes. In math, we say this means that they are similar. So if I take this particular right triangle and I dilate it about this point, I get a new right triangle. It's the same shape, it's just larger. All of the other transformations we've looked at produced figures that were congruent to their images. That is, they were the exact same shape and the same size. Dilations preserve the shape but change the size. In this lesson, the center of dilation, the point that we're getting bigger or smaller about, is always going to be the origin. This is going to make our math a little bit easier. So in this case, it says line A prime, B prime. That's right, that's ray A prime, B prime. It goes from this point here to this point here. Is the image of ray AB after a dilation. So we took AB and we made it bigger relative to the origin. So if I were to take this marker and show you, I could sort of draw a dotted line from the origin through point A, and I get to point A prime. I can do the same thing through point B, and I get to point B prime. It's like I'm blowing that line up. I'm making it bigger relative to the origin. This line here, from A prime to B prime, that's 4 units long. 1, 2, 3, 4. And this line here, AB, is 2 units long. So if we take the length of line A prime, B prime, we said that was 4. And we compare it, we make a ratio to the length of AB, line segment AB. I'm sorry, I said ray earlier. These are really line segments. We said line segment AB had a length of 2. 4 divided by 2 is 2. And so the scale factor in this case is 2. A prime, B prime is twice as long as AB. It's twice as high up on the graph, and it's twice as far over from the y-axis. If I want to describe the coordinates, how did coordinate A change to A prime? I just take the coordinates of A and multiply each of them by the scale factor. 2, the original coordinate of 2 times our scale factor of 2 is 4. The y-coordinate here, 2 times 2 is 4. So K in this case is what we call the scale factor. Now let's do an example where we start with a shape instead of just a line segment, and we're going to dilate that. So I want to draw a quadrilateral. That means 4 sides. Quad is 4, lateral is sides. With vertices, that is the corners of this thing. A is going to be at -4, 1. So I go -4, positive 1. That's my point A. B is going to be at 1, 3. So there's my point B. C is at 1, -1 here. And D is at -3, -1. D is down here. So here's our quadrilateral. Looks like that. That's A, B, C, D. And it says, find the coordinates of the vertices, that's the corners of a new image, after a dilation, so we're either going to make this bigger or smaller, having a scale factor of 2. Well, scale factor of 2, that means I'm going to double it. So this picture is going to get bigger. So to do that, we've drawn quadrilateral A, B, C, D. To dilate it, we're going to multiply the x and y coordinates each by that scale factor, by 2. So if a point in our original image has the coordinates x, y, the image is going to have the coordinates 2x, 2y. So let's try that with each of these points. A started out as -4, 1. A prime, -4 times 2 is -8, and 1 times 2 is 2. So those are going to be our coordinates of A prime. So we go -8, 2. So A prime is going to end up there. B originally had coordinates 1, 3. If we double both of those, we're going to get 2, 6. So if we go over 1, 2, and up 6, B prime is going to be up there. C was originally 1, -1. So C prime is going to be 2, -2. 2, -2. Down here, that's going to be C prime. And D originally was -3, -1. So that's going to be -6, -2. I just multiplied each of these by 2. So -6, -2 is down here. That's D prime. Now if I connect these, there's my new quadrilateral, A prime, B prime, C prime, D prime. Notice it has the exact same shape as our original quadrilateral, it's just bigger. Now, you're going to try checkpoint 1. In this case, you're going to draw a triangle, D, with the vertices, that is the corners, that are specified. You're going to have to draw DEF on here, and then you're going to have to find the coordinates of D prime, E prime, F prime, and in this case the scale factor is 3. So what I'd like you to do off on the side, just like we did in the problem above, we're going to keep track of what were the coordinates in the original shape and then in the image after the dilation. So the original had coordinates D was -3, 2, E was 1, 2, etc. Remember in this case that the scale factor is 3. So we're going to take these coordinates and multiply them by 3. So when D is turned into D prime, we're going to take -3, the original x coordinate, and multiply it by that scale factor by 3. -3 times 3 is -9. We'll take the y coordinate, 2, and multiply it again by the scale factor. 2 times 3 is 6. And you continue on. Please pause this presentation while you work through checkpoint 1. Next, we're going to explore what happens when you use a scale factor that's less than 1. When our scale factor is a fraction less than 1, like 0.5 or 1/3 or 1/8. So let's try an example. We're going to draw a triangle PQR with the following vertices. P is at -8, 1, 2, 3, 4. So there's P in our original triangle. Q is at -6, 6. And R is at -4, -2. So there's our original triangle. Then find the coordinates of the vertices of the image after a dilation having a scale factor of 0.5. Now that's a number that's less than 1. That tells us that we're going to shrink our figure down. We're going to make it a fraction the size that it started out. So in this case, we're still going to multiply the x and y coordinates of each vertex by the scale factor. Only in this case, the scale factor is 0.5. So if in the original figure, a point had the coordinates x, y, in our new image, it's going to have coordinates 0.5 times x, 0.5 times y. So -8 times 0.5 is -4. 4 times 0.5 is 2. So the new point, P prime, is going to be at -4, 2. That's this point here, P prime. So notice that P moved closer to the origin in this case. Our scale factor is a number less than 1, so our image is shrinking down towards the origin. Q, again, we're going to multiply each of these by 0.5 in order to get Q prime. So this is going to be -3, 3. -3, 3 ends up here. So there's your Q prime. -4, -2 is going to give us -2, -1 when we multiply each of those by half. And there we go. There's our R prime. So now here's what our new figure looks like. Again, same shape, just shrunk down towards the origin. Sometimes what will happen is that you're given an image and the result after a dilation, and you're asked to find the scale factor. So here's an example of it. And this is like if you ask why do you need to know about dilations, these are really important when you're designing computer graphics, especially in video games. When you want to give the impression of something coming towards you, you dilate its image using a positive scale factor. You make it look like it's getting bigger as it comes towards you. If you want to show the image of something moving away from you, you dilate it using a scale factor that's less than 1. You make it look like it's moving away from you. So an artist is using a computer program to enlarge this design. So we started off with a small one and made it bigger. We blew it up. And we want to know what's the scale factor of that dilation. How many times bigger did they make it? Well, remember we said that we can compare the length of a side in the original and the length of a side in the image. So let's look at this. The width of the original design, the distance from here to here, is, well, let's see, this goes from 1 up to 3. It goes from an x-coordinate of 1 up to an x-coordinate of 3. 3 minus 1, that's 2 units. It's 2 units wide. The width of the image, this thing up here, let's see, it goes from 3 all the way up to 9. 9 minus 3 is 6 units, so it's 6 units wide. So the scale factor is 6 units, the image, divided by 2 units, or 3. The image is 3 times larger than the original. Next, I'd like you to do checkpoint 2, which asks you to find the scale factor when a particular line segment is dilated. So we've learned a whole bunch of different kinds of transformations, different ways that we can change shapes in a coordinate plane. Remember that in a translation, each point of a figure is moved the same distance in the same direction. So if you started off with coordinates x, y, you would end up with coordinates x plus however much you moved it to the right, comma, y plus however much you moved it up. If this number is negative, that's moving it left. If this number is negative, that's moving it down. The next thing that we looked at were reflections. In a reflection, a figure is flipped over a line. If the line that we're flipping it over is the x-axis, then we take the coordinates of the original point, x, y, and the x-coordinate stays the same, but the y-coordinate changes its sign. If it's negative, it becomes positive. If it's positive, it becomes negative. We switch the sign in the y-coordinate. If what we're reflecting across is the y-axis, then the y-coordinate stays the same, but the x-coordinate gets flipped in its sign. The x-coordinate, if it was positive, it becomes negative. If it was negative, it becomes positive. The next thing that we looked at were rotations. In rotations, a figure was turned about the origin through a given angle. Remember, we looked at 90 degrees, 180 degrees in a given direction. We specified clockwise or counterclockwise. If we had a 90-degree clockwise rotation, which is like what's shown at the right here, the original coordinates x, y become y, negative x. In a counterclockwise rotation, if we go the other way, the coordinates become negative y, positive x. In a 180-degree rotation, if we start off with x, y, we end up with negative x, negative y. And remember, in this case, this negative means switch the sign. So if x started out as negative 1 originally, when you put a negative sign in front of that negative of negative 1, that would give you positive 1. Last, we looked at dilations. In dilations, a figure either stretches or shrinks with respect to the origin. And so if a point on that figure started out having coordinates x, y, after it stretches or shrinks, its new coordinates are k times x, k times y, where k is what we call the scale factor. And remember that if k was greater than 1, that was a stretch. The figure got bigger. If k is less than 1, that was a shrink. The figure got smaller. This is the end of the Chapter 13 lessons.